We are back to our discussion on longitudinal data analysis. I stress on the word analysis because we are now going to do the analytical part of the longitudinal data. Why we are going to use this longitudinal data, that I discussed with you in the last session, and its use or usefulness in practice has been fully stressed there, emphasized there. So now let us see that why the classical approaches, classical standard methodologies fail to provide strong statistical inference on longitudinal data. So to make proper use of the data is basically the purpose of the good statistician. So what I am going to do is that we stress upon that the observations or data that you obtain over different points of time are really correlated, because over time points their dependency occurs, and in the classical approach like analysis of variance or analysis of covariance, this is not really considered upon. So we try to look at that, try to incorporate the idea of dependency of observations over time points, and then go for the modern approach for analysis of this kind of longitudinal data. So in this section, actually I will consider the statistical analysis strategies for the longitudinal data I discussed in the previous. Okay. There are several strategies. I start from strategy 1, which is ANOVA. You know the meaning of ANOVA, right? This is analysis of covariance on the final measurement, adjusting for baseline differences, which is called endpoint analysis. What does it mean? Final measurement. Final measurement is the last time point measurement, and you have to adjust for the baseline time points observations, that is the first column that you have over the first point of time, right? Now, what you do is that you can think of analysis of covariance where the term covariate or explanatory character is basically the baseline. So you look for the baseline character as the covariance, and then go for the responses or outcomes as the final measurement observations, right. Then this is the analysis of covariance, and the second strategy is where analysis of variance can be applied, but little bit different with repeated measures. So I will explain that what is repeated measures analysis of variance. The strategy 3 is multivariate ANOVA approach, which may be beyond the limitation at this stage. We may consider it later on. And then strategy 4 is the most current approach, generalized estimating equation. The strategy 5 is the mixed model, which is a very prominent, very recent approach. And then strategy 6, which is modeling change. It's not the changing model, it's modeling change. Okay. So we will take up some of these, not all, because of the time constraints. All right. So you see that I said that this is the traditional approach, this is the newer approaches, and this is the most recent approach that we are going to consider. Okay. The things to consider is we always assume that the time intervals are equispaced. That means the repeated measures ANOVA, or for multivariate analysis of variance, we must assume that all observations or all subjects or all patients are measured at same interval of time point, okay? Because then our plots that we have shown earlier, that also shows in the similar manner. All right, then the second assumption of the model, basically the assumptions is that for ANOVA or ANOVA what we are going to use, we need to assume all these outcomes are normally distributed, and they have the common variance. So homogeneity of variances is a very basic assumption in ANOVA or MANOVA. All right. The second point is a little bit, I should say that additional, it's not that much required, because if you have the data set larger than 30, then automatically it is based on the normal assumption, because in view of the central limit theorem, the asymptotic normality follows. So you are able to apply the ANOVA technique if you have the data set more than 30. Another assumption is that univariate repeated measures, ANOVA assumes sphericity or compound symmetry. What do you mean by compound symmetry? I will be coming to that. Let's consider another issue. If time permits, we go for the missing data analysis. So where we need to impute the missing data. If any particular responses or outcomes are missing, we impute that by some strong scientific technique. All right. Then, as regard the compound symmetry, essentially the outcome variable are assumed to have common variance at each time point and common correlation between two different time points. So basically, this is called the compound symmetry problem. Now, once again we come back to the profile plot, where you see the variances at each time point. When you see the time point 2, time point 3, time point 4, there are variations. So the variances are different, and that we have to catch those variances. Now you see that how this differs. You see, there is a variation between individual to individual. So from the baseline, you see that there is a variation. Then if you go for that, you see, and over different time points, you see that. And finally, the outside arrow essentially indicates that this is the variance, maximum variance that you can get in time 4 for all the patients observed. All right. The question that arises, that does variance look equal across time points? The answer is, looks like most variability at time 1 and least variability at time 4. You see that the variation is most at time point 1 and time point 4 it is less. All right. So you can look back to that previous slide in the first session that we considered this kind of data for 6 individuals. We have different time points, the observations, and then you can compute the variance. You can compute variance within time point, within a fixed time point. So for time 1, the variance comes out to be, if you compute that, comes out to be 65.6. For variance 2, time point 2, variance is this, and for all these time points, the variance could be considered. As I said, that the graph or the plot shows that at the first time point, the variance is highest, and then it goes down in the second time point, but it goes a little bit up in time point 3, and then again the minimum variation that can be observed in time point 4. Right? This is the correlation structure that is obtained from the data against different time points. So how that indicates that how time 1 and time 2 are the observations we obtain at time point 1 and time point 2, how strongly they are correlated, right? This value indicates this thing. So you cannot ignore that. You cannot ignore and go for straightaway analysis of variance. That is the beauty of longitudinal data analysis, where you can take into account the correlation between the observations at different time points. All right. Then let's go back. Go to the compound symmetry. This should be. If it is compound symmetry, the structure should be like this. For analysis of variance, if it is a compound symmetry, we assume that compound symmetry always occurs. So it should be the structure like this, where the correlations are all same, like 1, 2, 2, 1, 1, 3, 3, 1. All these correlations are same, and variances are 1. But you see, look back to the previous data set, that longitudinal data set we have. This is not the compound symmetry problem. So we need a different type of analysis for that. Talk a little bit about the missing data. As I said, that if time permits, we will go for the more general discussion on missing data. So if there are some of the observations are missing in the longitudinal data, we just try to fill in. But you see that what is the problem is that, like if you longitudinal data, if you observe the 50 people at time point 1, you get that the measurements, and because of the missing you get for time point 2 only 35 people, then it's not balanced, you cannot compare them. So that's the problem with the longitudinal data where missing occurs. So one has to take into account scientifically the missing data, incorporating the imputation technique in such a way that the imputed values are pretty much close to what you expect to be there, right? So this missing data imputation is very important. You see that here we stick to, as I said that in the particular case, we stick to very simple last observation carried forward strategy, LOCF, and other strategies will be discussed if we consider the missing data analysis section. Okay. You see that LOCF, last observation carrying forward, means in the third time point for subject 1 the observation is missing, fourth time point observation is missing. So these observations are missing means you can think of the subject 1 drops out, he or she dropped out because of maybe his or her health condition, or got disgusted with the medication and other things, the side effects are there and other issues are there, family problems are there. So all these problems can prevent him or her to come back and report. So the observations are missing, right? And then so what to do? This is the LOCF technique where the last observation has been carried forward 1313, and similarly it has been filled in this way. So this is the LOCF. Now we go back to the strategy 1, the endpoint analysis. Remember I said that essentially we think of a single point time point measurements, the last one, the final one, time point 4, the observations that you observe, and ignore the intermediate time points observations. So and you think of the baseline measurements as your covariance part in the ANOVA model, right? So let's see that how you can, if there are two groups are there, as I said that in the first session, the two sets of data, like for A you have 3 individuals, for group B you have 3 individuals, then you can go for the analysis like this. I am not giving the code for that, but if you use some code in SAS or any other standard software, you can see the sources like this, and the in view of 6 observations you will get only 6 individuals, I should say. You get 5 total degrees of freedom 5, and you can compute that the sum of squares and other things, and this is the sum of square due to time, sum of square due to group, all these things. And also you can compute at time point 4 A and B, their mean time, least square mean, and then can compute the T statistic, student statistic there for drawing your inference. So in most of the situations, in fact in all the situations, you see that the p-value is higher than 0.05 or 0.05. So all these cases, the effect you want to test is insignificant. So this is the you can study that thoroughly and can look at that that how this endpoint analysis can give you the basic inference on the model consideration and the group to group variation and other things. All right. So the question that comes up after the endpoint analysis, that overall are there significant difference between time points? That is difficult to say because we are not considering all time points, we consider only the last column, last time point, and the baseline. So intermediate time points are not considered. So we cannot say that using this endpoint analysis. the next question that comes up, overall are there significant changes from the baseline? That's also we cannot say, because baseline is taken as the covariate, and over time points the measurements are not taken into consideration. And then the question that do the two groups differ at any time points? The answer is from the analysis that they don't differ at time point 4. The fourth question is, do the two groups differ in their response over time? That also we cannot say, that over time point we have not studied that. So endpoint analysis is a very limited procedure where you are not able to draw strong inference. Now we will go for strategy 2, where I said that the repeated measures ANOVA is considered, and if you go for the naive analysis, I rather go for the ANOVA table here, and then can think of that. You say that for individual you have time point 4, that is the basic data we have taken up at the very outset, and then you consider this between times the variation, and you can compute the SS between times. So variation between times can be taken into consideration, and that is 224.79, right? And similarly within time also can also be considered, and that is computed to be 676.17, and then we can similarly, using simple code in SAS or any other software, we can get this thing done. All these model, error, corrected total SS, all these things can be computed here. And because now in the ANOVA table we are able to consider 4 time points, so degrees of time variation, SS due to time, that gives you 3 degrees of freedom, and this 224 just previously we computed that can be seen to ultimately can be seen to be compared with the errors degrees of freedom, and that is also insignificant value is obtained. So in both the situations the inference is insignificant. I mean, there is no effect of time, there is no effect of model and other things. Now, but we have not talked about the repeated measures as yet. So if you go for repeated measures, so between subject variation can be computed, between times variation can be computed. Still there is in the error part, earlier it was 676.17, now it is reduced because of the between subject variation. So you have, even though you apply the same drug to say every individual, but because of the body chemistry, body reaction, every individual cannot give the similar response. So there is a variation, and this between subject variation can be taken up through this line. So the unexplained variability between subject variation is this, and the unexplained variability, now the error degree of freedom is, error SS is reduced quite a bit from 676 to 399. So this is how the repeated measures have been taken into consideration. Okay. Now if you think of two groups, before that I did not talk about the two groups. So within a group there are 3 subjects. So you have 2 groups A and B, 3 subjects each. So you see time 1, time 2, time 3, time 4, and group there are 3 individuals in a group A, similarly in group B. So SS between times could be computed as earlier. Now between groups you can consider. So the more you are considering the variation, taking up the variation, the more the error degrees of freedom is being reduced. So now you can compute the SS between groups, and that comes at 126.04, and so this way you can reduce your SSE, and I can show you the whole table once again. So this is how one can get the similar table taking into consideration now the extra factor came up, the group, the time cross group interaction. So, this has been taken up here. So, this is how the degrees of freedom is all, the degrees of freedom has been broken up, like these 7 degrees of freedom has been broken up 3, 1, 3. So, the model vary error sum of square has been broken up into 3 parts, altogether is this 377, right. So, this is the univariate repeated measures rANOVA and repeated measures ANOVA, and once again for the groups you see now the error degrees of freedom, instead of, because now time and time cross group interaction goes to the error. So, error degrees of freedom altogether, earlier it was something more than that 399 point something, now it has been broken up into 3 parts, and that error 373 is now smaller. I mean their sum of square is less than earlier situation. So, what I am going to say over that because you considered between group variation, that reduces the error, then you considered the time in group interaction, that reduces the error. So, this is how the error degrees of freedom can be broken up into several sum of square due to time cross group, due to error and other things. So, the comments are like this: overall, are there significant differences between time points? The answer, now at least we can look into that, because earlier we did not look into that, only the last column has been taken into consideration. Here all the time points have been taken into consideration. So, the answer is no, time not statistically significant. If you look back the previous table, you see that the p value is quite large. So, time is not statistically significant. Overall, are there significant changes from baseline? No, time is not statistically significant again. And so, although in the plot you see that there is a change over the baseline, change in the mean response over the baseline, here in the statistical analysis it really does not exhibit that. Next question is, do the two groups differ at any time points? No, once again the answer is no, p value is quite large, that we can see from the previous table. And do the two groups differ in their responses over time? No, not even close, although in the plot we should see that they are close by in the time point 4. So, these are the my implication is that my objective here to demonstrate in that way that even though from the plot you see something that the variation occurs among the individuals, even among the two groups, but in practice while you go for rANOVA, repeated ANOVA, while you go for analysis of covariance, they are not able to account for all these variations. So, the rANOVA is totally failure, or the ANCOVA is totally failure in properly analyzing the longitudinal data. In strategy 3, we consider repeated MANOVA table. In the repeated MANOVA procedure, the multivariate observations are to be considered. So, there are more than one dependent variable, and multivariate approach to repeated measures treats response variable as a multivariate response vector. So, the repeated measures are considered as the multivariate response vector, not just for repeated measures, but appropriate for other situations with multiple dependent variables. Let us look at the table first of all to try to understand this scenario. So, you have a table where for two groups in the earlier data set that we discussed, we take difference from time 2, difference between time 2 and the baseline, difference between time 3 and the baseline, difference between time 4 and the baseline, that are all given in the 3 columns of the difference. All right. So, based on this we want to apply the rMANOVA, and objective is that if you want to test that differences like difference 1, difference 2, difference 3 are 0, it indicates that essentially over the baseline there is no change in the response pattern over different time points 2, 3 and 4. So, if the null hypothesis is accepted, so it does mean that there is no difference virtually between different time points. But if it is rejected, then one has to go for that which time point is really responsible for the rejection. Now, it is automatic if you apply this in SAS and get the testing procedure, and we want that we applied that in SAS software, and we got ultimately the statistics. Different types of testing procedures are there for MANOVA, and incidentally all these MANOVA gives us the same inference that hypothesis is accepted. So, over time points there is no difference virtually. So, from our MANOVA analysis what we get is this: overall, if the question is like that, overall are there significant differences between time points? The answer is no. Time not statistically significant because p value is quite large. Overall, are there significant changes from baseline? The answer is no. Time not statistically significant. Do the two groups differ at any time points? We cannot say. The MANOVA cannot be able to say that. Do the two groups differ in their responses over time? No, not even close. The group and time interaction can be seen to be insignificant. So, this is the summary of rANOVA and rMANOVA which require imputation of missing data, and then rANOVA requires compound symmetry, which is very ideal situation. Normally this situation does not occur. Then requires subjects measured at same time points, but easy to implement and interpret. There are some other modern strategies which need some more basic or foundational concept on that, like the generalized estimating equation, maximum likelihood estimation procedure and imputation technique.